Okay. Thank you everyone for joining today. Welcome to new specifications for stainless steel structural design. We are very happy to have you here today. Just a couple of housekeeping things. If you have any questions, please save them for a Q&A session in the last 10 minutes of the presentation and post them through the Q&A chat. Also, if you are seeking AIA CES credit or continuing education credit, please stay on for the duration of the entire webinar. All right, thank you. Our speaker today is Ms. Catherine Houska. She is a renowned international expert on architectural and structural metals. She has published over 190 publications, has lectured around the world, and worked on many very cool, prominent projects. And today, I am from the International Molybdenum Institution, and we are co-sponsoring this webinar with the Nickel Institute. We are industry trade associations formed around some of the alloying constituents in stainless steels, namely nickel and molybdenum. So without further ado, I'm going to pass it over to Catherine, and please enjoy the webinar. Thank you very much.
Hello, everyone. Thank you for joining us today. I'm assuming you can see my screen. Thank you, Carly, for the introduction. I'm going to go straight into this. As Carly mentioned, you will get AIA credits or continuing education credits if you stay on long enough. The materials in the presentation are copyrighted. And some disclaimers. Everything that I'm going to say today is a suggestion for your consideration. It is not a recommendation. We are simply trying to provide a high-level overview of a really complex topic. Our learning objectives will be to review the contents of the new AISC specifications and the revision of SEI ASCE 8, which should be coming out and not too long, as well as the new AISC code and design guide. We'll learn about the families of stainless steel that are used for structural applications and some of their differences with respect to corrosion performance, mechanical and physical properties, as well as talking about the fundamentals of alloy selection, which are covered in the AISC publications at a basic level. And then we'll also talk about, show some applications where stainless steel is being used structurally and the reasons for its selection, with a few case study examples thrown in, like the US Air Force Memorial that I'm showing on this slide. It will be high level, with our goal being to direct you toward resources that will be helpful to you as you delve into structural stainless steel and capitalize on these new resources. It seems important to start with some history. We don't want anyone to think that this is a completely new concept, using stainless steel as a structural material. And I have to say that North America played a huge role in the development of structural stainless steel applications. The first large structural application for stainless steel in the world was the Gateway Arch. And it was, by tonnage, the largest application for 30 years. And because of its design, it inherently goes through cyclic loading and is just fine, having been involved in the 50-year inspection. Because there wasn't enough structural research, there were formal requests by professional organizations that more research be done before the arch was built. And that occurred, and it delayed the start of construction a bit. Because that research was available, it was used for some other things in between, like the Unisphere, which was built for the 1964 World's Fair. You've probably seen it in a few movies. As it was blown up by aliens and all sorts of things. It's made a lot of cameo appearances, but it was built by the stainless steel industry for the World's Fair to show all the stainless steel product forms that were available in 1964 and promote stainless steel as for structural design. There have been demonstration buildings to get stainless steel into codes around the world, but the largest and in the first really large building framing application was in Canada, the Canadian National Archives in 1995, designed for a 500-year design life to withstand earthquakes, tornadoes, whatever might be thrown at it. And so structural framing is not a new application. And we certainly see it in some very corrosive industrial applications like pulp and paper plants. Industrial applications are by far the largest current application for structural stainless steel. Over 90% of the market is in industrial applications. And I'm showing two examples here. And because of that, what's typically used in industry is what you tend to find on the shelf. We'll touch base on that a bit later, but there's growth in a lot of other applications in response to issues like the need for resilience, which will be the topic of next week's webinar, if you're able to join us. It seemed important to start with a basic comparison. Carbon steel, alloy steel, stainless steel, what do you use where? Clearly, you know, if you can use carbon steel, are able to protect it and regularly inspect it to keep it protected, it might be your most cost-effective choice. Alloy steels, because you're adding alloying elements, are more expensive. And you get improvements in corrosion resistance, ductility, and energy absorption and weldability. But if you really have a corrosive application and you need the best ductility and energy absorption that you can attain, and good weldability, then stainless steels are really your best choice. And it's really a matter of whether or not the application is a logical one for it. So I'm going to talk a bit more about the families of stainless steel a bit later in this presentation, but did want to point out that the range of corrosion resistance is significant within the stainless steel families. There's also a range of performance in terms of energy, absorption and strength. So let's delve into some of this. Starting first, for anyone that's new to stainless steel, with what is stainless steel and how does it work? Well, it's iron-based with at least 10.5% chromium and low carbon. So that's a distinction between stainless and other steels. And it is stainless, not stain-free. Of course, you can achieve stain-free if you use a much more corrosion-resistant stainless steel and clean it as necessary, depending on the application. Sometimes it just doesn't matter. You just it will give you a long enough life without having it be stain-free. Corrosion resistance is attained primarily through the chromium, molybdenum, and nitrogen additions, while nickel greatly improves formability and weldability. That's a generalization, but a basic rule of thumb as you're looking at different stainless steel alloys. With carbon steel, we see gross corrosion over the surface, rust. With stainless steel, the chromium allows formation of a thin passive film. And unless the environment is too severe for that passive film, you don't see corrosion. And then when stainless steel does start to corrode, we see pitting. Here I have a surface that did have corrosion staining on it that I cleaned off to photograph what these pits look like. It's quite different in appearance from the layered gross corrosion of the entire surface that you see in carbon steel. It seemed a good idea too to point out some other differences. With carbon steel, we have a defined yield point. With stainless steel, we don't. This gives you a comparison at low strains of the austenitic and duplex stainless steels, carbon steel, and 6061 T6 aluminum. And at high strains, again, you can see the comparison between these structural materials. Stainless steel has better energy absorption than either aluminum or carbon steel. And we will delve into that a bit later. There are also differences in mechanical properties. We have more information on this in the AISCE specification and the design guide, but it is, you can see that the strength of the duplex stainless steels is significantly higher than for austenitic stainless steels, and also higher than a typical grade 50 carbon steel that you might be using. It's also very important to note the differences in thermal conductivity and thermal expansion, especially if you will be combining different steels or steels with other structural materials. The coefficient of thermal expansion for the duplex stainless steels is closer to that of carbon steel. Well, the austenitics are further, actually quite, close to that of copper. So you can see that this is something that you also need to consider during design. So in the carbon steel world, AISC 360 has been the specification that I'm sure you're all familiar with. Through AISC 370 was modeled on that, but specifically for stainless steels. And the title of the specification is Structural Stainless Steel in Buildings, but it's intended for any application that is loaded as you would a building. We had to develop a code of standard practice specifically for stainless steel because the carbon steel code of standard practice, which determines what is necessary in terms of fabrication and handling and those kinds of issues, wasn't appropriate. We needed something very specific for this material. There's also been a lot of work on revision of ASCE 8. This was the first structural stainless steel specification in the entire world, developed as the direct result of that research done to justify the Gateway Arch. And it's been 20 years since it's been revised. Like the AISCE publications, it will include duplexes now, which had not been the case previously. The design guide which has been around for a number of years, has also been revised and significantly expanded to be an even greater resource for you. So let's focus on this AISC library of stainless steel. These are the publications. If you're an AISC member, you can go and download these for free. I do encourage obtaining copies if you don't already have them to guide you in your work. So the scope of AISC 370 includes everything that's heavier products: hot rolled, welded, extruded, open structural sections, round and rectangular, HSS, plate and bar. It does not include seismic design, some of the shapes, composite members, or HSS connections, other than a limited scope. Part of this was simply what information we had available, and there is active work occurring to add these to the next version, because certainly stainless steel has been used for seismic design for some time. It focuses on design in, the common design issues that most structural engineers face as they use stainless steel. The properties, specification, selection, and how they differ from carbon steel: tension, compression, flexure, shear, various loading conditions, mechanical and welded design, fire resistance, fabrication, and erection. We do in 370, but also in general, think that it's important for you to understand some of the differences in terminology. If you're used to working with carbon steel, you're going to encounter some of these things. First of all, if you're talking to someone in the stainless steel industry, you might hear the word grade on regularly throughout the conversation. And if you're a structural engineer used to carbon steel or alloy steel, you're going to think strength grade. In the stainless steel world, grade has been used to mean alloy composition. So this can be a source of confusion. There is only one stainless steel standard in ASTM that actually has strength grades. That's for laser and laser hybrid welded stainless steel structural sections. But otherwise, the term, grade means alloy. So make sure that you're talking about the same thing. Stainless steels are grouped into alloy families, and they have different microstructures, different mechanical and physical properties, and the corrosion performance can be different in different service environments. So, if you have a particular type of exposure, that may steer you toward a specific alloy family. It's also critical to understand that stainless steel gauges are not defined by any standard, and they can be a bit different from one stainless steel producer to the other. On top of that, if for example, somebody was talking about 10 gauge stainless steel, well, that is not the same thickness as 10 gauge carbon steel. So please make sure you specify the actual thickness that you want. Don't use gauge numbers. We also, because stainless steel is not going to be protected, always start with corrosion resistance. And then once we see what's available at the level of corrosion resistance that we need for the service environment, look at the mechanical and physical properties and other considerations. So the families of stainless steel that are covered in AISC 370 are the austenitics and the duplexes for all structural sections, The precipitation hardened alloys only for tension bars and fasteners. They are the least corrosion resistant of the stainless steels, but they do provide the highest strength. I should note in ASCE 8, we also include the austenitics and the duplex stainless steels. The duplexes are a new addition that were not in prior versions, and we also brought it up to the state-of-the-art knowledge of structural stainless steel in ASCE 8, which hopefully will be published soon. I thought I'd show an example of one application for austenitic stainless steels. U.S. Air Force Memorial, that's 3/4 inch welded 316L plate. And those spires are moving constantly. So lots of cyclic loading, which was part of the selection of an austenitic stainless steel. It was completed in 2006. So in general, if you need a higher level of corrosion resistance, that means higher alloy content, which is going to increase the cost. It is important to, I'm sure you're probably doing life cycle analyses, but ultimately you're paying a bit more money for something that will not have to be replaced, that will not shut down that production line or put people at risk, depending on the application. Mill finishes, the standard rough mill finish, generally pickled and abrasive blasted, that you get does not add to the cost. But that is a rough finish. And if you, for either aesthetic reasons or for corrosion resistance reasons, need a smoother finish, that will add to the cost. And some finishes that you might be familiar with on light gauge products simply aren't going to be available on a typical structural section. The common austenitics are more available, like 304 and 316. And the duplexes are, however, often more cost effective. They also provide better chloride stress corrosion cracking resistance, crevice corrosion resistance, have significantly higher strength. Of course, it depends on the application as to whether you can capitalize on that. And there is less movement during welding. So if you have a more complex shape, then it is easier to weld a duplex into it. There's less complex fixturing required. If you need very sharp, precise corners, then you probably need something that's laser or laser hybrid welded, as opposed to traditional welding or roll forming. So those are some basic considerations for specification that may or may not be different from what you're already doing. The San Diego Harbor Drive Bridge was one of the world's longest self-anchored suspension bridges, but also the first duplex stainless steel pedestrian bridge in North America. So as I mentioned previously, when we start the selection process for alloys, we have to start with corrosion resistance requirements. And there are some significant differences between families and within families in terms of corrosion resistance. Then we look at mechanical properties and followed by availability of that specific stainless steel alloy or alloys that you may have identified and that product form. But we also have to look at the manufacturing process. If, for example, you could have used either an austenitic or a duplex, but the shape is complex, that might push you towards using a duplex. The physical properties, of course, have to be considered as well, and dependent on the application. AISC 370 does provide in-depth requirements for everything from ordering to design, fabrication, quality control. 313 is the Code of Standard Practice, covers erection and fabrication. AWSD 1.6, of course, is the structural welding code for stainless steel. And it is, I'm going to note that it is important not just to call it out, but to look at those relevant sections, because they're often things that you have to specify within D1.6. This gives you the overall product range. Really, you can get any product form that you could get in other steels, in stainless steel. It may not be, you know, what's stocked is more limited, but you can get it. New Polyplaza is an example of cable tension systems for glass. 316 cable, 2205 for the tension bars and spiders, just to show that not all applications are industrial. This slide summarizes what you can generally obtain for you know, custom, and I should know, custom fabrications and short runs are readily available. As long as that particular alloy is in inventory at a service center, the industry is focused on those custom fabrications and short runs, often to meet demand. For laser and laser hybrid welded structural sections, there are sizes that are commonly stocked. The beams can go up to 50 inches, and channels also can be obtained in for large sizes. If you need something that's heavier than 2 inches in thickness, then you're generally going to go to built up plates from, you know, using other welding methods. Of course, you could have that in a lighter gauge as well. But if you need really large beams, their laser welding won't work as an option. Hot rolled shapes generally come in up to 6-inch sizes, but larger sizes are sometimes available. Extruded shapes generally have to fall within an 8-inch diameter, but that maximum size really varies with the alloy as to what can be obtained. Hollow sections are very readily available because of their use in various industries. There's a table in AISC 370, A3.1, that shows which specifications you need to be using, which ASTM specifications you need to be using. And generally, there are at least 2 that you will need to call out when you specify material. One for chemistry and mechanical properties, and the other for tolerances, finish, handling, everything else. Sometimes you need to use more specifications depending on what you are specifying. I'm going to focus a bit on one of the requirements in section A. Within A, we not only have part of specification in our requirements to look at specific types of corrosion and consider it during design. And related to that, we also expect the engineer to look at the atmospheric environment to collect information to determine which stainless steel is going to be most appropriate. And there is a table in the commentary that provides some very specific guidance, specifically for atmospheric environments, continually or regularly immersed, in industrial environments, so that you know what questions to ask before you speak to a corrosion specialist. As we talk about corrosion, I do regularly see drawings where stainless steel is all that's called out, perhaps because there isn't knowledge about how broad a range of corrosion resistance is provided by different stainless steels. The chemistry of the stainless steel can be used to calculate a pitting resistance equivalent number. This is a relative ranking. It is not something that tells you for every application which stainless steel will perform better in that specific environment, but it does give you a relative ranking. The higher the number, the more corrosion resistant the stainless steel. The precipitation hardening stainless steels are the least corrosion resistant. Then you'll see 304, 316, the lean duplexes up, as we go up in the mid 20s. 2205 is a big jump up with 35. And then they're both austenitics and duplexes that are up in the 40s. So that's a big range of corrosion resistance, ranging from stainless steels that may well have staining in many atmospheric environments to those that could potentially be immersed in seawater and never corrode. So there is selection information within 370, as I just mentioned. Additional information is in the Design Guide 27. On top of that, there are both producer and industry association literature sources and websites. We also have a whole library of stainless steel information that you can download. And then as you delve deeper, there are books and papers and symposiums put out by the organizations to which the corrosion specialists belong to. And then of course you have metallurgical engineers who specialize in specific types of corrosions or specific environments. So you don't have to make all of these determinations on your own. There is a lot of atmospheric corrosion data available. I'm showing some from South Africa as one example, as well as data that has been, research that's been done on specific industrial environments. This is interesting because you can see for three different stainless steels, Corten and mild steel, in different environmental severities, how very different the corrosion rates are. Of course, galvanic corrosion can be an issue in practically any structural application if you were going to combine different metals. So it's critical to separate the metals. Otherwise, whatever you're pairing stainless steel with will selectively corrode. The gap that you need isn't that much, but any surface burrs or non-uniformities could still connect them. So you have to consider the best way of separating and something that will be long-term. You also need to consider surface area ratio. If you have a large surface area of stainless steel and a small surface area of the more anodic material, the less corrosion resistant materials such as galvanized steel, then that small surface area metal will corrode at a highly accelerated rate. It's not the stainless steel that is going to be sacrificed. It will be the less corrosion resistant metal. Now, if on the other hand, you have a large surface area of Corten, as I show in the one image, and stainless steel fasteners, that they're unlikely to increase that corrosion rate. One of the more famous galvanic corrosion failures in a structural application is the Statue of Liberty. They did know about galvanic corrosion in 1886, and there was separation between the puddled iron and the copper. But it failed pretty quickly. Within 20 years, they were regularly making pretty significant replacements to the iron, particularly in direct contact with the copper. By 1986, it really simply needed to be rebuilt. So the first, as far as we know, the first large duplex stainless steel structural application that was not industrial was the duplex stainless steel sections that are between that center core and the copper. So everything you see in the space between that core and the outside is duplex stainless steel. The armature bars, those that directly support the copper, are type 316. They have a similar coefficient of thermal expansion. And in many applications, probably wouldn't have to separate them, but they were galvanically separated. But, you know, since this work was done, nothing more has been needed, as opposed to ongoing significant repairs that started pretty quickly after it was first built. There is a book about that in case you're interested. So we start with section A 3.1a and in 370's commentary, which includes a table that I'm going to walk you through some examples of, so you can see some of the data that you need to collect before you call a specialist, so that they have a good picture of what that environment is likely to be. Here are a few examples of applications exposed to atmospheric corrosion. Really, any building or structure exposed to outside air, whether it's sheltered in some way or fully exposed, sprayed or splashed with water, but not immersed, exposed to pollution, but not part of an industrial product line, is generally an atmospheric application. And these are some of the pieces of data that you need to collect to better understand that service environment, such as pollution exposure, salts, acid rain, the time of wetness, in that, how much rain there is, how frequently are these thunderstorms, will anybody be cleaning it? And, it is important to note that not only 60% of the US population, but 60% of the world's population is in a coastal zone. And many people assume, unless if you're not right by the coast, that they're not coastal. But everything that's in maroon in this graph and this map has a pretty high level of salt exposure. This is from the U.S. National Deposition Program. Anyone can log in and actually go to a specific point and see what the salt levels have been measured and over time in a particular location. Additionally, in the US, 70% of the population is in a location where there is at least some de-icing. If you have both, that makes the problem more complex. De-icing is used anywhere where there's icing, snow, etc. in most of the world. So it does need to be considered. Some of these salts are more aggressive if they're concentrated, and it can travel quite far. Research done in Illinois showed dry salt particles traveling up to 1.2 miles from roadways. I worked on a project that was a rural campus, and the closest source of de-icing was a highway 2 miles away. It's all a matter of how far the wind is going to carry the particles. And it can be found quite high in buildings. In industrial environments, we are looking at somewhat different factors, the atmosphere, like the gas composition, what chemicals it's exposed to, presence of sulfides. In regularly or continuously immersed applications, we are focused more on the chemistry of the fluids, the water, or the process fluid where there might be exposure. Here are some common applications: a lock and dam, desalination, wastewater treatment plants are all common applications, in addition to industrial process streams. When you have to look at the chemistry of the fluids. And sometimes these applications are also exposed to the atmosphere too, but you want to know the chemical composition, the pH, whether they're chlorides, the temperature, the presence of microbiological organisms. So really you need to get as much information as you can about those fluids and the range of temperatures that it might be exposed to. I should note there is a lot of data out there about the performance of stainless steels in different fluids. This happens to be sea and brackish water. Please don't forget to consider whether an application might be exposed. This was what happened to New York City after Superstorm Sandy. And their tunnels were immersed for weeks and weeks. So if that is likely, you need to consider it during your design process. These are railings that are regularly going to be splashed. And when I've talked to people around the world who are making decisions about railings, I regularly hear that painted carbon steel railings, even painted annually, tend to fail within 8 to 10 years. So there has been a big shift towards using stainless steel for some of these applications. I'm showing a picture from Hudson River Park. That's 316 Ti. I should note that in areas where there is splashing, there is staining on those railings, but it's not going to affect the structural integrity. It just doesn't look as nice. In the Canary Islands Park, because of the rocks right beside these railings, they are exposed to far more salt spray. The mock-up that was put up initially in type 316 showed significant staining in a short period of time because of that. This was a salt spray test. So they used 2205 with a mill finish, and it's performed well for over 30 years. AWS D1.6, the structural welding code, has been mentioned. It covers all the basic requirements, but there are things that you will need to specify within it. So please don't assume that you can just call out D1.6 and be done with it. It is comprehensive. It does include welder qualification and other requirements, and austenitic stainless steels, common ones, are what are pre-qualified. There is discussion about pre-qualifying duplexes, but we're not there yet. And but it does cover the requirements for welding of all stainless steels. If you're going to be welding stainless steel to carbon steel, then you use D1.6. Stud welding, D1.6. Common welding methods that you're used to with other steels are all used for stainless steel. And I should note that these are beautifully welded, large structural stainless steel beams at the top. And then at the bottom, an image that I took when doing an inspection. I was underneath these beams in a seismic zone, and every weld I saw would have failed based on, well, numerous issues. So I kept praying that there would not be a seismic event while I was underneath them. The lower image, nobody checked the welder qualifications, and they were not qualified to weld stainless steel. So the nonlinearity of stainless steel does lead to some things that you need to consider, and I'm going to talk a bit about that. First of all, because there is not a defined yield point, as you would have in a carbon steel, stainless steel is far more ductile, and you have much better toughness, so it can absorb a lot more energy without fracturing. This shows you, again, the same comparison that we saw earlier in the presentation. The area under the curve is how much energy can be absorbed, and it shows you the ductility of the steel. And that's critical for resilient design. They're talking about seismic, blast, impact, toughness. And, I think showing those areas filled in can be helpful in seeing the relative differences. Of course, that is used on a regular basis. If you've got stainless steel bollards, you're not just selecting them because of, you don't want to have corrosion and maintenance. They will absorb a lot more energy than the carbon steel options. Quite several of the buildings at the former, the World Trade Center site have used 2205 structural sections, vertical structural sections, at least at the lowest level of the building, to provide a more effective barrier. This shows the toughness of welds, but generally shows that austenitics, why austenitic stainless steels can be used down to cryogenic temperatures. The duplex stainless steels are a bit better than carbon and alloy steels, but nowhere close to the austenitics at very low temperatures. It's part of why austenitic stainless steels are what is used for LNG tanks, among others applications. Stainless steel, well, we don't include seismic events in 370 right now. There is a good reason why stainless steel is used for seismic applications and why we're working to add it to 370. The Golden Gate Bridge is, 2205 is going to be used for seismic retrofits for it. Once the funding comes through, it's already been approved. But there are many other applications that show the performance of stainless steel in seismic applications. Fire and thermal radiation resistance is another advantage of stainless steel. It depends on the application as to how much benefit you achieve. So this looks at strength retention with increasing temperature. Of course, aluminum is a low melting point material, so we don't expect it to provide good performance, and that's part of why it's being replaced in some building applications because of concern about fire. You can see initially the stainless steels lose strength faster than the carbon steel, but once you're above about 600 degrees, then the austenitic stainless steel are better. And really, it's the austenitic stainless steels with molybdenum are better. So the other key factor that is considered is stiffness retention. And here you can see that stainless steel is definitely superior to carbon steel, and which can mean in some applications, if we're not talking about very high temperature fires, such as might occur in an industrial application, that you can often use stainless steel without fire protection, which is part of why we see it in some of these building applications as a bare metal that is essentially jewelry on the building in addition to providing structural integrity. You do need to consider the differences in thermal expansion if you're combining metals, so that everything moves together, or you're allowing for those differences in movement to make sure those fire doors open. I wanted to review a few resources for you as we come to the end of our presentation. I'm showing the AISC and specification and code of practice and design guide, ASCE 8. The new version is expected out hopefully this year. AWS D1.6. These should be part of your library. There is a 3-part webinar series that you can get to on AISC's website. This presentation was only intended to be a starting point for you. And we do encourage you to watch those webinars. They are for credit. There are some articles that have been published in Modern Steel Construction that also are wonderful resources. For technical help, the Nickel Institute has a great helpline, and that link will be in the chat. You should be able to see that and follow it. And in addition to other information on the pages on NOMOA's website, which I encourage you to look at, there is a PDF library with over 550 publications that you can simply access and download for reference for you and your colleagues.